Hi guys, BuildZoid here, and today we're going to be taking a look at what kind of performance you can squeeze out of an RX 9070 when you don't have any of the usual restrictions. So, no power limit and proper voltage control. So, anyway, let's get into it. Now, the card that I'm using for this is an XFX RX 9070 Swift OC edition, which I bought. So a big thank you to the channel supporters for making the purchase of the GPU possible. If you'd like to support the channel, there are links in the description that you could check out. That would be very much appreciated. And then for the power limit, I have a video on how you can disable the power limit. Then for the voltage control, I'm using an Elmore Labs EVC2 SE, and I have a video explaining how to hook that up to most AMD GPUs, and on this card, the XFX Swift AMD RX 9070 OC, the header for that is right over here, and it's conveniently labeled, so you don't even have to figure out which order the pins are in. So that's cool. And anyway, so let's get into it. So in the background, I have the oscilloscope, which is going to be acting as a glorified multimeter for monitoring the core voltage. Technically, we do have control over SoC voltage and VDDCI and memory voltage. Unfortunately, and based on my testing, those other three voltages don't help anything. And if anything, they make things worse. So yeah, unfortunately, now I'm not sure if this might be, like, this could be a limitation of the Hynix GDDR5 memory chips. Maybe the Samsung GDDR5 chips are more receptive to increased operating voltages or decreased operating voltages. But yeah, with the Hynix memory chips, you do anything to the memory voltage and it just, like, at best, it gets, well, at best, nothing changes. At worst, things get worse. So, yeah. Anyway, so basically the only voltage control we really need is core voltage, which is why the oscilloscope is only monitoring core voltage. Then down here, I have a total system power readout because I was too lazy to hook up something to just monitor the GPU power consumption. And unfortunately, due to the power limit removal mod, the software power readings from the GPU are not very accurate. So, yeah, I mean, we still have one power reading, which is kind of vaguely where it should be, which is this right here. But the total board power reading, that one's just completely wrong because of the power limit removal on this card. So, yeah. Anyway, let's get the EVC2 set up. So here's the EVC2 software. Technically, you could run this off of the system that has the GPU in it. I'm running it off of my daily system, right? So the system that's actually recording this video, that's the one that's also running the EVC2 software. But yeah, technically it could also be running off of the same system that has the RX 9070 in it. I'm not really sure that there's any major downsides to that. Anyway, so I'm hooked up to the I2C2 header. So that's what we're gonna go to. And then we're gonna set this to MP2868. Find devices, we find 22 and 24. Now, with this card, occasionally I've had issues with the controller address 22 not showing up, but usually just like scanning it a bunch of times would eventually get it. So, yeah, that's just like, I think it probably has something to do with like the GPU driver talking to the controller, and if you just get unlucky, it won't show up. Anyway, so we're going to be adding 22 and 24. Now, 22 is the one controlling core voltage. 24 is the one so 22 controls core voltage and VDDCI, so that's the memory controller voltage. Whereas 24 is controlling VSOC and memory voltage. So, yeah, we don't actually care about 24 because, like I mentioned earlier, messing with SOC and memory voltage unfortunately doesn't lead to any benefits. So we're just going to be using 22. And the only things we really care about are vid offset, and then the load line gain, which I'm going to be increasing because, like, I'm not 100%, well, so far in my experience with overclocking this card, it's usually better to increase the V-droop rather than turn it down, has been my experience. Because turning it down, while it does give you, well, so we'll not get into that. Just like it kind of depends on the GPUs. For Nvidia cards, you generally want like basically no V-droop, and on this card, I've found that it actually seems to behave a little bit better with more V-droop. So we'll leave it at that, as I don't really feel like explaining what like V-droop in detail right now. So, but of course, we need a baseline. So we're not going to mess with anything just yet. We're just going to run the card with no power limit because unfortunately, I did not opt to use switches for the power limit. Like, technically, you could do that power limit modification with switches. I've just jumped the circuitry. So the card permanently has no power limit. Anyway, I'm just going to check that the card is actually at stock. Okay, I'm just going to set it to default for now, just in case. And then we're going to go back to 3D Mark, and we're just going to run that. Anyway, so there you can see the core voltage, and without a power limit, the RX 9070 runs at just about 1 volt, as you can see from the average core voltage reading right here. Technically, you could also kind of judge it from the voltage level on the oscilloscope, and what you'll kind of notice about this is that this line is a horrible mess, and that's normal. It's also one of the reasons why, like, tuning voltages on CPUs and GPUs and using software voltage readings is not, like, depending on the hardware, is not really that representative of what's actually going on. Because, yeah, the average voltage might be, a volt, but you'll notice that the maximum voltage is peaking at just under 1.2, and the minimum voltage is 0.9-ish volts, right? So we have quite a spread on that 1 volt average. But that's completely normal. And actually, my card is running better than factory as far as especially the maximum voltage goes, because I've added a whole bunch of capacitors to it. Though from an overclocking perspective, the maximum voltage actually doesn't really matter to us very much. Yeah, and you'll also notice that the noise pattern that the GPU produces varies depending on what kind of workload you're running. And fun fact, you can actually count the frame rate from the noise pattern itself. You can also sometimes catch frame drops if you have an unstable GPU, as in like you'll just see the pattern just disappear for like 1 frame. But 9070s don't really do that. That's more of a NVIDIA thing in my experience. Like usually if 9070 is unstable, it'll just straight up crash. It won't start really like dropping frames or anything. So anyway, yeah, you can see our system power draw is about 500 watts right now. Obviously that's at the wall, so you need to account for power supply efficiency, which I think I'm using I'm using either a gold or a platinum PSU, so it's somewhere around 90%. So realistically, we have like 450 watts actually going into the system. Some of that needs to go to the CPU and the motherboard, and the rest of it goes to the GPU. So right now we should be, I think, around 300 watts. And we can actually check with hardware info. Like, it's not going to be accurate, but, it's going to give us a rough indication of if we're kind of close to... is the problem with the total graphics power reading in hardware info over here. So this power reading over here, yeah, so 291 watts for the maximum. So the problem with this reading over here is that this only takes into account the core voltage, the memory voltage, the SoC voltage, and the memory controller voltage. But there are other power rails on the GPU, and also technically the fans pull some power. Which is mostly like, well, actually, before the power limit mod, that is actually a concern. Like the fans will eat into your power limit. If you crank the fan speed to 100%, the fans will actually eat into the power budget for the GPU, which is really silly, but that's just how GPUs are nowadays. So yeah, like like technically you could put the fan power delivery like before the shunt resistors, but I don't think I've ever seen a GPU actually do that. Um, but anyway, so yeah, about 291 watts. And the score we're getting right now is, of course, 28,600 points, which is a little bit on the lower side of scores that this card produces, but I'm going to guess that's just because hardware info is running in the background and stuff. So, yeah. Um, it's actually one of the more annoying things with the 9070s is that they'll sometimes, like, the boost algorithm on these is a little bit too clever. And so sometimes you'll not get as much boost as, like, you should be getting. And sometimes you might be getting a bit more than you should be getting. Especially once you start, like, pushing the card to its limits. But anyway, so we're going to switch over to custom. And we're just going to start with the memory because there's unfortunately not really anything I can do about that. The memory basically maxes out at 2800, and I can run fast timing, so that's what we're going to run. And then I guess we're just going to run it in this configuration just to see what the memory does on its own. So 28,000, what was it, like 28,600 points. When I first got the card, the very first Time Spy score that I ever got out of it was, I think, just under 27,000 points. So just removing the power limit and not touching anything else already boosts the performance a bit, because from the factory, RX 9070s have an extremely low power limit, right? Like this card from the factory is 245 watts, whereas a bone stock 9070 XT is 304. Which is just like AMD's way of forcing some product separation between the cards, because the fact that they cut a few of the cores out wasn't making enough of a performance gap, so they also lowered the power limit. You know, I maybe should have used Steel Nomad instead of Time Spy, because Steel Nomad is faster. The thing is, you can push Time Spy further, so... And also, like, it's a more popular benchmark. At least for now. So anyway, just overclocking the memory didn't really help as much as I thought it would. I was kind of expecting it to be just just over 30,000 points. So okay, let's check the temperatures, because it's one of the things that, well, I wonder if the thermal paste wore out already. Because yeah, I have been running the card pretty hard. Oh well. The thing is, I've not actually checked what like the normal operating temperatures are for it, so I'm not sure. Anyway, so that's the memory overclock. Now let's get to the core. And actually at this point I'm just going to start ramping up the fan speed. Okay, that's... So the way the way I'm setting it up right now is so that it like ramps really hard as soon as the benchmark starts. Actually, because it runs at like 50. Yeah, so we actually need to move all of these points like way over here. Because it's idling at like 30, and as soon as it like starts running 3D mark, it should hit like 50, and I want it to basically ramp to 100% then. Or close to 100%. Okay, well, we're not gonna... There, that should do that. Anyway, so now we're just gonna do the usual voltage offset slider. And the thing you should, like, notice is that, you know, so far the card has been running at around, like, 0.99 volts or, like, just about 1 volt. You'd think, oh, minus 100 millivolts on the voltage offset slider is going to make the card run at 0.9 volts. Except it won't, because that's not what the voltage offset slider does. It doesn't actually offset the core voltage itself. It offsets the frequency curve relative to the voltages. So, yeah, we're at minus 100, and we're at still basically a volt. Unless I forgot to press the apply button. The reason I'm saying unless I forgot to press the apply button is that I was actually expecting it to sit at 0.98. Oh, but I set it to minus 100. Okay, so that actually makes sense. Yeah, it's like at minus 150, it should end up at like 0.98. But anyway, so yeah, you set it to minus 100, and like if you're on the power limit, it might actually lower the operating voltage. But if you're not hitting the power limit, it is not going to lower the voltage. It's just going to raise the frequency. Which means it's also going to raise the power consumption a tad. Or in this case, not change it at all because the operating voltage is basically the same. Technically, like, as the operating frequency goes up, the voltage should come... Well, I don't have a power limit, but if you did have a power limit, the voltage offset slider will sort of lower the voltage. Like, it still won't lower the voltage by as much as the, like, driver says. Like, if you set minus 100, you're not going to get 100 millivolts less core voltage. But you're going to get a bigger voltage decrease than what we're seeing here, because as the frequency increases, the actual, like, the power scaling is basically linear with frequency. So if you raise the frequency by 10%, you can basically expect the power consumption to go up by 10%. But of course, there's a power limit. So if we want to raise the frequency by 10% and stay under the same power limit, that means the voltage has to get reduced by like 5%, because the voltage scaling is quadratic. So if you increase power, like if you increase operating voltage by 10%, you get a 21% increase in power consumption. If you increase frequency by 10%, you get a roughly 10% increase in power consumption. So if you're hitting the power limit and you move the frequency curve down relative to the voltages, so you get higher frequencies at lower voltage points, the voltage will come down a little bit and the frequency will go up a lot. Your power consumption won't change, but you'll get more performance. But personally, I'm just kind of annoyed that it's labeled core voltage offset when it's more like a frequency offset rather than an actual voltage offset. But yeah. Anyway, so this should put us over 30,000 points. You know, I guess one of the things that's affecting this testing is that the room is probably warmer than the last time I was pushing this card. So now what we're going to do is we're going to just start adding a bit of voltage, like 45 millivolts. Actually, no, not yet. Not yet. No. We want to, first things first, we want to max out the offset, but we don't want to crash the card, because if you crash the card, the drivers get a bit strange. So, and I want to avoid that. But basically, like, so if you're overclocking one of these and you crash out of a benchmark, sometimes it's fine, but sometimes the boost algorithm will basically break and you have to like restart the computer several times before the boost algorithm like recovers itself. And when that happens, like you basically end up with overclocking not working at all. Like you'll have like weird performance issues when trying to overclock after a crash that like breaks the boost algorithm. So that's just something to keep in mind. Anyway, so yeah, at minus 150 millivolts, we're getting 0.98. Well, 0.975, which is 0.98. So yeah, we're not getting 150 millivolts less core voltage. We're getting like 20 millivolts less core voltage. Way higher frequencies, though, which is why the performance is going up. But yeah, it's not actually lowering the core voltage that much. Yeah, I guess the card really is running a bit warm today, because with these settings that it's on right now, it should be getting about 31,200 points, and we're a bit low. Or it's just hardware info running in the background that's screwing it up. But anyway, so now we're going to actually start raising the core voltage. So to do this, so one of the sort of annoying things with these cards is that they have a really deep like idle state. So you'll notice that the core voltage is basically 0 if there's nothing going on, right? Like if I move the mouse around, the core wakes up, but if I'm not interacting with the system, the GPU basically doesn't run the core power rail. Which makes tuning the core voltage kind of annoying because you can't actually see how much extra voltage you're getting. So we're going to run the GPU-Z render test because that keeps the core up and running. And here you can very clearly see how much V-droop there is, because we zoom in on this a bit. You can basically see that like we have like idle, and then the dip here is the core actually working to render a frame of the GPU-Z render test, and then it goes back up to idle. So, or like, it's not actually idle, but it's like relative to the workload, it's idle, right? Because obviously I was also describing sitting on the desktop with nothing running as idle, and okay, you get the idea. But anyway, so now we're going to start raising the voltage a bit, and the funny thing with these cards is you can't just skip to like plus 150 millivolts because it like the boost algorithm gets very confused. So you basically need to walk them up to like high voltages. Um, so I just gave it 25 more millivolts, and we actually need to actually not 25, just 20, because for some reason this card like comes with plus 5 millivolts from the factory. And anyway, so yeah, we're gonna give it plus 25. So now instead of 0.7, we're getting 0.726. And now we're gonna run Time Spy again. And what's wacky is because of AMD's boost algorithm being, well, the way it is, even without touching anything in the drivers, we just run this again, the score should go up. Because the way, and the funny thing is, this isn't a new thing with the RX 9070. Like the 5700 XT does this, the Vega cards do this. If you take a Vega and you just give it more voltage, it just boosts higher. Unfortunately, Vega cards are a bit prone to boosting so hard that they crash when you do that. But yeah, they do just boost higher. So anyway, now we're back at around a volt when actually running Time Spy. Power consumption's going up. We haven't increased the voltage very much yet, so the power consumption hasn't gotten particularly high just yet. But depending on how things go, we might end up with more than 700 watts of total system power draw by the end of this video. The reason I say depending on how things go is I think the card might be running a bit warm right now, so it might stop scaling before we get to that level of power consumption. I really probably should have done this with Steel Nomad. Would have taken less time. At least it's not Firestrike. Unfortunately, Firestrike is so old that it just doesn't load these cards properly. I mean, Time Spy kinda also doesn't, but... yeah, like, Firestrike is really old. Oh, we just went over 600 watts. I kinda missed it, because I wasn't watching the power readout. Oh, and over 600 at the very end. So anyway, now we're at 32,000 points. Whoa, that jumped a lot. Yeah, so this is what I was talking about with like the boost algorithm on these cards being kind of whack. I wasn't expecting it to jump up this much, but I guess the boost algorithm woke up and decided that, hey, I got 25 more millivolts to play with. Let's go fast instead of kind of slow. Anyway, let's check what hardware info picked up while that was running. So no, that's core power. So 327 watts. So now we're pulling like well, actually not overclocked. You can get some 9070 XTs that'll have like a 300, I think 40 watt power limit from the factory. So you know, we're approaching like stock 97, like overclocked base, like factory overclocked 9070 XTs, I guess. There, that's the way to put it. Core temperatures are still holding fine, but I do have the fans completely cranked, so that does probably makes sense. Yeah, because I was kind of worried because when I've pushed the card to the absolute limit, the hotspot can get up to around like 110-ish. So being at 93, I was kind of worried that we were going to hit that way soon. But yeah, that's not going to be happening for a while, evidently. Anyway, more voltage. Because yeah, that is actually all there is to this. So now we're going to go to... Okay, so we went 30 millivolts. Let's go straight to plus 60 millivolts. And see what that does. Now, what you'll also might notice is that the peak to peak is actually getting worse and worse as the average voltage gets higher, and that's just because there's more current driving the transient overshoot and undershoot. So like the upward spikes are getting progressively taller the more average voltage we have. But we can actually sort of tune that down with V-droop. So right now we're on stock V-droop at 54.688%. When I pushed the highest score that I managed on this card in TimeSpy, I did that with I think 70% V-droop. So a roughly 50% increase over the stock V-droop setting. I did also experiment with reducing the V-droop, and that didn't really seem to help anything. So the funny thing with like the V-droop tuning is that like your average voltage actually doesn't really depending on the combination of V-droop and voltage offset, you can end up with the same average voltage, but the big difference is at high V-droop settings you get less peak to peak, whereas at low V-droop settings you get very high peak to peak. And theoretically, especially if you're getting a lot of undershoot, that's not ideal for stability. And also, I kind of suspect that the boost algorithm is very, like, I don't know how fast it is, but on NVIDIA cards, it's already at, like, millisecond timescales, and I can't imagine that this is any slower. So, one thing I've been actually wondering about is that if the, like, high V-droop with high voltage offsets, because you can run, like, low V-droop and low offsets, and that technically gives you, like, the same average voltage. But if you run high offset with high V-droop, you also get the same average voltage, less peak to peak though, and I kind of suspect that it might actually give you more boost. Because the card will boost, like, the boost algorithm is so dynamic that, like, in low load scenarios, so when it's not pulling so much current and there's less V-droop, it'll boost more, especially if it sees more voltage. So, I kind of suspect that, yeah, like, a high V-droop, high voltage offset combination actually works best for these cards. But it's also kind of really hard to test for. Anyway, we're now comfortably over 600 watts of power draw. Oh, and again with the... Actually, you know what? When I said we're approaching like stock 9070X, like factory overclock 9070 XT stock power draw, I was actually wrong. Because I forgot about all the other minor power rails on the card, right? So like a 340, we probably, like the card was probably pulling over 340 watts, especially when you consider that the power reading over here, where is it? Yeah, where is it? Oh, right, total graphics power. This is not going to be super accurate because it's relying on power readings from the power stages, and like, they're not, like, this card does use smart power stages. They're supposed to be pretty accurate for current monitoring, but they're not on the same accuracy level as, like, shunt resistors. They just can't be. So, yeah, we're probably, like, at this point, we're definitely pulling more power than a stock 9070 XT. We're also just under 33,000 points. GPU hotspot is 97 degrees Celsius, which I think is still fine. Obviously, I don't know that I'd, plan to like daily this configuration, but that's not what we're interested in here today. Today we're interested in maxing out 3D Mark Time Spy. So anyway, at this point, I'm going to actually give it a bit more V-droop, and that's going to lower the score. So we're going to go from our 54.688% to, like, Let's go to like 62. That's going to lower the score a bit, but it's also going to lower the average voltage. And it's going to lower the power consumption. So then we can run more offset. So that's kind of the thing, like your immediate reaction might be like, oh, but the voltage is like getting lower. And it's like, yeah, that's on purpose. So I think at this point we're probably gonna see like 32,000-ish points. But like the previous run with the 54% V droop was averaging, occasionally around 1.04 volts. So we're also down like a few millivolts. The issue is that the average voltage is not like representative of the minimum voltages, and the boost algorithm is very fast. So, yeah. Unfortunately, I haven't found a way on the oscilloscope to like target like, because the funny thing is the average voltage right now is like, if I'm actually just going to stop it right here. So if I pull up the cursors, right? So, so if I set this one AY to our average, that's like here, right? But this second line is the actual like high load scenario, right? So you'll notice that like the average voltage is like, because the average includes all of these like upward spikes and low load situations, whereas the high current draw, that's this part right here. So yeah. And so I think for the actual score, this part right here is what most affects the overall performance of the card. At least I suspect that's the case, because I don't really have a good way of verifying that. Though I think if we zoom in a bit, yeah, so you'll notice like here we have like low V droop. Here we have some like partial load scenarios, so it like drifts around a bunch. Anyway, so we got 32,404 points. So now we're going to just give it back more voltage again. So instead of 60, we're going to go up to 90. And we're just going to run again. And I'm going to take the cursors off. I'm going to go back to our 5 milliseconds per division. Open all of these back up. Now, the funny thing with the V-droop is as you have more V-droop, the voltage offsets actually get less effective. So plus 30 like going from plus 60 millivolts to 90 millivolts at 63% V-droop is not the same as going from 60 millivolts to 90 millivolts on 54% V-droop. It's actually less of a voltage increase because as the operating voltage increases, the output current increases, and so the V droop increases with the output current. And that's how I ended up at like almost 200 millivolts of positive voltage offset with 70% V droop for my top score with this card. Actually, I'm gonna get this out of the way, because personally, I actually find the voltage waveform more interesting to watch than Time Spy. So what's kind of interesting to me is that on certain voltage configurations, this card will have like a weird sort of like instead of having this like nicely defined section right here, it'll actually have a bunch of like upward spikes in that, which I believe is some kind of micro throttling going on. If the boost algorithm thinks that it's like starved for core voltage. Um, but yeah, and the funny thing is the card seems to do that from the factory. Though I'm not sure if that's because I like the issue is I have quite a few modifications on this card at this point. So I'm not sure if that's like expected behavior or if that's like just my card at this point. Um but anyway, let's give it more voltage. I'm going to go up another yeah, let's go to plus 110. Just going to check our max temperature. Also, core clocks, the score is back up to where it used to be. So far, the max clock was 3,380 megahertz. The thing with the core frequency readouts on GPUs, well, we have also this effective readout, is that since, like, I'm not sure how susceptible AMD GPUs are to this, but since, like, the 900 series for NVIDIA, the core clock readout is not necessarily representative of performance. And so personally, I don't really pay much attention to this on GPUs because if the FPS doesn't go up, then the core clock is imaginary and doesn't matter. Right? Like if core clock goes up, but FPS doesn't go up, then the core clock is a useless metric and we don't need to pay attention to it. Anyway, temperatures are still well controlled. And this is actually, I think, one of the like one of the other potential benefits with the high VDROOP setup is that the scenarios where the GPU is pulling the absolute most current, the voltage is actually lower, and so it doesn't get as hot, right? Whereas if you have very little VDROOP, the GPU is running at basically the same voltage all of the time, and so even when it's getting absolutely slammed, it just ends up getting really really hot. Um, so yeah. Anyway, so we're gonna do another run. And I think at this point we might see 3.4 gigahertz in hardware info. Also, this is like a lot of people have been like, oh, this max frequency offset slider, it doesn't do anything. Yeah, the reason it doesn't do anything is that from the factory, without external, like within the limitations of what you can do with a factory condition card, you're not hitting that max frequency, like the stock max frequency, you're not hitting it. So obviously, raising this doesn't do anything because you're not hitting the frequency limit, right? Like you haven't even reached it yet. Um, so anyway, we're just going to run like this. Now, the funny thing is once we get into really high voltages on the over here, is that we're actually going to we might already be at that point where we can actually lower the voltage offset even more. But we're not like I'm not going to start doing that until the temperatures start getting kind of out of control. So not yet. So there's like a whole sort of so when you're like overclocking these cards with external voltage control, you have that whole like raise the voltage and then lower the offset and then raise the voltage and lower the offset. And they sort of like feed into each other. Yeah, and what you'll notice right now is that the actual average voltage hasn't really changed very much right now. And I suspect, um, And this is a thing I've definitely seen on NVIDIA cards, is if you volt mod NVIDIA cards to just have voltage offsets, the driver will fight you. So if you like try to raise the voltage by 50 millivolts, the driver will lower the voltage request to the VRM by 50 millivolts. So you'll end up at the exact same voltage as if you didn't have a volt mod. The AMD driver doesn't seem to be as prone to doing that, but I do suspect that it does do that a bit. Because previously we were running like 1.04-ish volts, and I just raised the voltage from 90, like plus 90 millivolts to plus 110, and so you'd think, oh, we'd be getting like, I don't know, 20, 25 millivolts more. Like, yeah, I have a lot of V-droop, so we're not going to get the full 30 extra millivolts. Oh, wait, I went from 90 to 110, so that's not going to be plus. Oh, actually, so, yeah. Well, even then, like, the voltage is a bit lower than I thought it would be. So I do suspect that there is a bit of a, like, you raise the external offset and the driver actually lowers the voltage request a bit, as well as, like, the V-droop playing a role. Which kind of leads to just having absolutely insane voltage offsets on the voltage controller, which is not ideal, because when the card crashes, the voltage, like actually hits the like max vid request with the with the full offset, which yeah, can get kind of high. You know, I should put the trigger on this so that it doesn't bounce around sideways so much. That's not really helping. All right, let me make it downwards. There we go. And we finally got over 33,000 points. So of course what we're going to do now is just raise the voltage again. I do wish this was a little bit less brain dead than just like raise voltage, get more score. But like the boost algorithm is kind of, you know. Oh, so we hit 3.397. Power consumption at this point is where I keep losing track of the power consumption readout, which is quite amazing. It's not like there's that many sensors. 361 watts. That's not as high as I thought it would be. Output current on the VCore VRM is 287 amps, which is fine. Like the current limit on the VRM is 330 amps, so we're nowhere near hitting that. And actually, the VRM temperatures are, which we should have a readout for that. 70 degrees, 69, which is actually a pretty nice temperature. But we are running short benchmarks, so that little 8 phase is kind of it's getting pretty hot. Now the thing is, I don't know if it's close to hitting thermal equilibrium, but we are only running tests that are lasting like a minute each. Well, okay, the second test is almost 2 minutes, but yeah, so in a daily scenario, I think I would probably want a more substantial VCore VRM than the little 8 power stage 4 phase that we've got here. But this is still perfectly acceptable. And that's one thing, like, that's kind of a funny thing to keep in mind with, like, extreme overclocking, is that because in actual extreme overclocking scenarios, the benchmarks are so short, you can get away with slightly underpowered voltage regulators because you don't, like, it takes time for things to overheat. They don't just overheat instantly if you run them too close to the limit. So, yeah. Anyway, I did apply the new voltage offset, so I guess we'll just run again. Actually, you know what? I'll give it a bit more. I want the score to go up faster. And we're still, like, yeah, we've still got thermal headroom as far as I'm concerned. Now, I think the limit for this card is a little bit under 34,000 points, but I don't remember. It would be cool to hit 34,000 points, though. Because that would be a whole 25% faster than the, like, stock score that I got out of this card. Admittedly, not sustainable for, you know, day-to-day operation, or probably not sustainable. Maybe if you had the card on, like, water cooling, you could get away with a setup like this. Because, like, really, that's the main concern is just the temperatures, in my opinion. I don't think we're pushing the voltages that high. Oh, and I guess on this PCB, also the voltage regulator is kind of a concern. Yeah, especially if you were going with one of those water blocks that only cools the core. Yeah, this PCB would not be ideal for that. But if you had a 9070 with a full cover water block, so also water cooling the VRM, then actually the VRM temperatures would not be a concern whatsoever. Because water cooling voltage regulators is just massive overkill. It's actually one of the ways you can get the nominal current rating out of your various power stages, right? When a power stage has a nominal current rating of like 60 amps, under most operating conditions, that's not a practical amount of output current because it's going to produce too much heat. Unless you water cool it, then it's not a problem anymore. Now this uses 850 amp power stages for VCore. So I mean, again, yeah, like the water cooling would deal with it. And actually, yeah, that's basically the thing is we're not actually going to get the card to pull 400 amps ever, as far as I'm concerned. But if you really did want to put, you know, the full rated current of the power stages through them, water cooling them would basically be the only way to do it for any like sustained amount of time. Okay, so now we've hit the point where the score stops going up as quickly with voltage increases. So we're going to try lower the voltage offset a bit to like minus 165, which is going to do very little. But it shouldn't crash just yet. Actually, I might give it like 5 millivolts more. There we go. So now what you're going to start noticing is that the actual like core voltage stops really going up at this point. Also, what's kind of crazy to me is how the minimums are still like 900 millivolts. Right? Because that's basically the minimums that we started with. I wonder if there's like... I'm kind of wondering if maybe that's like intentional on the GPU's part. Are we gonna... we're over 700 watts. Now, again, you have to consider that, like, so when we started the video, the card would be pulling around 530-ish max. Or, well, the whole system would be pulling 530-ish max, and now we're hitting, like, 700, so that's, what, 170 watts more power consumption? We have to consider that that's after the 90%-ish efficiency of the power supply, so the actual power draw increase on the GPU is probably somewhere around 153 watts, which makes sense. So we're probably, like, the card's probably pulling around 450 watts right now. Something like that. Because at the start, it was probably pulling around 300. And the score is going to be 33,300. Yeah, so so now it really slows down on the score gains. Okay, so we're going to go... I'm going to give it more V-droop, and then we're going to give it a whole bunch more voltage. Actually, maybe not that much more voltage. Maybe just, like, there. I wonder what kind of frequencies we're hitting. Yeah, we're still at 397, so actually at this point, maybe touching the max frequency offset will actually do something. Go to plus 25. Because the funny thing is like, if you just, like, smash it over... Like, I think I've read some guides for overclocking these cards where it's like, oh, you can just, like, raise this by, like, a crazy amount and it doesn't do anything. And it's like, yeah, because you're not actually getting anywhere near the max frequency. But in this scenario, I'm like, I do believe that if we just set this to, like, plus 100, there's a chance that the card will try to go at 3.5 gigahertz and it will just crash. So we're not going to just go plus 100 because that would not be ideal. Because again, like, if you crash one of these cards, depending on how badly you crash it, the drivers can get weird. So I would like to avoid that here. Well, it looks like I kind of nailed the amount of extra voltage I need for all that V-droop, because we're getting roughly the same average. Minimums are still 0.9, though. Now, the peak-to-peak at, like, 380, I mean, we are at 2 milliseconds per division, so that kind of skews the peak-to-peak reading. So yeah, we're at around 400 millivolts peak-to-peak, but it is worth noting that, like, this level of peak-to-peak is actually achievable at lower voltages if you just run way less V-droop. One thing that's kind of annoying that you might have noticed is that these cards actually ramp the voltage at the start of the test. So, like, when the benchmark starts, the core voltage will be actually kind of low, and then it'll ramp up. And the reason I say that's kind of annoying is because the card basically runs the beginning of the benchmark at a lower frequency. So the boost algorithm on these cards is, like, walking the frequency into the workload, which on one hand is great for stability, because the funny problem with Vega, which has a similarly crazy boost algorithm where it's like, oh yeah, you give it more voltage and it boosts more. Vega has a problem where it likes to start benchmarks at incredibly high frequencies and crash on the first frame. Like, it basically overboosts right at the start. The RX 9070 really doesn't do that ever because it ramps up slowly, though you can still, though it does usually also crash pretty quickly. Interestingly enough, these cards don't really produce a lot of artifacting, like some other cards. And I've not even seen, like, a lot of frame drops. Like, I have managed to push the card into situations where it's like, you know, it'll drop a frame or two. But, like, it's not on the level of, like, I've seen some cards where you'll be seeing, like, a frame drop every, you know, couple frames, or the typical thing with a lot of older GPUs is you'll just get artifacting all over the place, distorted geometry, flashing pixels, snow, you know, all kinds of visual artifacts. And meanwhile, these cards, like, these really don't seem to do that because the boost algorithm seems to just, like the card either runs or it doesn't. It doesn't really do anything else. But yeah, we're really at the point where the score just refuses to go up at this point. What are the temperatures like? 104. We still haven't gone over the 3.4 gigahertz limit. So you know what? I might give it a little bit more max frequency, and I might lower the voltage offset again. And go to plus 55 and minus 175. And I'm going to give it a little bit more core voltage. Because we're still okay on temperatures. Like, that's why I decided to go with Time Spy, is it doesn't actually run that hot on these cards. There are other, like, Port Royal on this thing is crazy. Like, right now, the max current draw that we're seeing is, where was that readout? 296 amps, and we're at, like, pretty high voltages. Port Royal hits 300 amps at lower voltages than what we're running right now. Port Royal is just absolutely insane with how much power it pulls and how hot the card gets. Evidently, AMD's like, well, I guess we're just not using a bunch of circuitry that ray tracing does use. And so, Port Royal ends up running way hotter because it's ray traced, whereas Time Spy isn't. So anyway, hopefully this doesn't crash, because if this does crash, we might be in for a ride trying to get the drivers to reset properly. Now, it's worth noting that the minus 175 offset that I have in the driver right now, that literally, that would never work without a bunch of, the extra core voltage that I've added with the EVC2. Actually, I'm not, maybe it would also not work with the same, if I had a different V-droop amount, but that has been, a thing that I've noticed with these cards is that, this card, because I don't have multiples. I wish I did. I wish I had one card that I didn't do anything to, just to use as, a sanity check. But, cards be expensive. And for some reason, nobody wants to send me review samples. It's just I don't know, well, actually, I'm not sure if they wouldn't be against sending me review samples, but they don't give me permission to attach oscilloscopes to them. So, not really that useful. But anyway, that is one thing that I would like to have is just comparison cards to see if some of the strangeness that I've noticed with this card is every card, or if it's just this one, or what's up with that. But anyway, the thing is, you basically, as you add extra voltage externally, you can run lower negative offsets in the driver. And of course, the core voltage doesn't actually change very much, and the power consumption goes through the roof as your core voltage goes up. So, yeah, it's not like we're somehow magically making the card undervolt better. We're not undervolting. We're just getting more frequency out of it. 3349. And hey, we finally broke the 3.4 gigahertz barrier. For whatever that is worth, because again, that frequency readout, I don't know how accurate it is. Though the score is barely changing, so I guess that's probably pretty accurate, because yeah, we're not increasing the frequency very much here. Just looking at the score, right? Like, if the frequency was going up a lot, you'd expect the score to go up a lot, which it isn't, so the frequency can't be changing that much. Anyway, let's see if maybe raising this more doesn't help, and let's give it a little bit more voltage, and I'm a little bit more droop. See what that does. I think this might actually regress the score, this combination of adjustments, because I don't think... it's only 2%, so... Well, let's see. You know what? I'm going to zoom the scope way out so we get like a better view of the ramp when the second test starts. Unfortunately, it also looks like a big fat yellow line right now, but... Oh, well, can't do anything about that. But now, like, you'll see the, like, ramping behavior for the start of the benchmarks. Yeah. Yeah, and you can see how it, like, ramps up, which is really not ideal from a, like, score perspective. Great from a stability perspective. Like, I much prefer this behavior to what Vega usually does, which is hits max boost on the first frame and crashes. So the annoying thing with Vega is that you can actually achieve higher average frequencies if you start raising the clock speed after the benchmark is already running. Because, yeah, honestly, as like a overclocker, I would like nothing more than the ability to turn off the boost algorithm. Because, like, why, like, for like gaming applications, it makes perfect sense why it behaves the way it does, and honestly, I think it's kind of cool that, you know, it like walks its way up to full speed. But from a like tuning for max performance perspective, this is really inconvenient. Because the benchmark starts in like, you know, like starts at like lower performance than it should. Okay, that did actually make the score go down a bit. I wonder what kind of frequencies. The thing is, okay, so we still aren't seeing anything more than 3419. And effective clocks haven't changed. Yeah, that makes sense because we're basically getting the same score. So, now the funny thing is the actual average voltage in the benchmark was pretty high. Because like towards the end of GT2, we were seeing like 1.08 volts. I'll try a little bit more negative offset, though 5 millivolts in the driver, like, I don't think that's good. I don't expect that to make much of a difference to the score, to be completely honest. But anyway, let's run again. And I looking at the runtime of this video, I now realize that my hopes that, you know, I could get to like the limit in like 30 minutes were misplaced, but well, that's how it goes for my videos. I'm still really wondering, like, what is going on with that, like, massive downward spike right there. Like, it's always 900 millivolts. Like, I bet even if I decrease the amount of V droop, it'll still bottom out at 900 millivolts. Because in my experience, like, decreasing the V droop on this card just, like, raises the overshoot, and it doesn't really do much for the minimums, which makes sense. Like, that's usually how you'd expect it to work, but... No, that didn't do anything, so... How about 10 more millivolts of offset? The funny thing is, it might, like, at some point it might crash. And effective frequency hasn't changed. Yeah, so it's still... Which, the score actually went down, so... It's not really that surprising. Max core temperature... You know, we're not even running the card, like, that hot. Like, yeah, that's hot, but it's not the hottest run I've ever done with it, so... Um... Yeah, let's try plus 195. It's interesting that it reaches like the highest voltage towards the end of GT2, even though that's like the highest power consumption part. Like I would have really figured that that's where the boost algorithm would actually like start backing off on the core voltage. Well, right now it's at 1.06, so that's not super high or anything. Actually wonder where the like fat part of the, or like the high voltage part of this is. Oh, yep. It's at like 990 millivolts for the really high current draw part. I mean, there's also that, like, massive, like, this part right here, but I don't actually know what that is. This right here, though, I know for sure is very high current draw. Unfortunately, I don't have the current monitoring stuff, or, well, yeah, current monitoring stuff hooked up right now. Huh, so that didn't help the score at all. We seem to have hit the limit, basically, at this point. Really, though. Yeah, 3419. Effective clock went up, like, ever so slightly. Core temperatures are still not that crazy, so... Yeah. Hmm. Thinking what to do. It seems like at this point the boost algorithm really, like, if I just keep, like, it really doesn't want to go up in voltage. Even if I raise it, so... I don't know, we might try lower the V droop a little bit and see what happens then. Though, I'm not sure. Thing is, I think this will, like, send the temperatures skyrocketing. And the minimums are still 900 millivolts. Oh man, we're almost at 1.1 volts. Yeah, 1.09. Also, due to how the oscilloscope is hooked up, it might be reading... Actually, it might be reading a little bit low. Because it's hooked up to the back of the GPU core, so obviously it doesn't see the exact voltage that the core is seeing. But also there's a 50 ohm termination at the scope, and there's like a slight ground potential difference between the scope and the GPU. So that's also not helping. So the core voltage readings on the oscilloscope, they're not exactly like spot on. Okay, so that is, I think, about as high as my previous best. Okay, and max temperature, oh, now we're at 107 degrees. Uh-huh. Okay, I'll try lower the V droop a little bit more again. And just run it again. You know, I guess one thing I should try is like a super, like try max out the card on like Though I kind of already tried to do that, and it didn't really seem to be working very well, because the temperatures were just insane. But like a very, very low V-droop run. The thing is, like, when you set the V-droop, like, even to, like, 30% or something, like, right now we're at, like, 400 millivolts peak to peak. At, like, 0 offset with 30% V-droop, we'd already be over 400 millivolts peak to peak. So, I'm not exactly thrilled about that. As far as, like, voltages go. We're actually getting so much peak, like, so much overshoot now that it's, like, clipping on the top of the oscilloscope. So we're not even seeing the full peak to peak, I guess. The thing is, like, with this card, at some point you basically hit a wall where the boost algorithm doesn't want to boost any higher, even if you, like, try to give it more voltage or whatever, because it's just detecting, I'm guessing, like, a thermal limit internally, and it just won't when it gets to that point. I mean, I guess we could still try more negative voltage offset in the driver, but yeah, I'm not sure about that. Also, we just hit almost 750 watts. Oh boy. Okay, we're probably going to have 110 degrees hotspot at this point. Because them voltages are really high and that power consumption is also just... It might be at like 500 watt GPU. Yeah, we're probably at like 500 watts on the GPU. Hey, it went up by 30 points. But at what cost? Oh, we're still at only 109. Effective frequency is at 391. Max frequency still hasn't gone up. Core current is at 308 amps. Oh boy. Yeah, and there you can see the current limit. No, actually, as far as I know, it should just like power throttle at that point, which we could avoid by messing with this right here. If you lower this a bunch, it'll lower the reported lower the reported current draw. But obviously, that's also going to break, like that's also just going to break power monitoring even more so. Anyway, at this point, hardware info is reporting 390 watts of GPU power draw. So yeah, we're probably okay. We might not be hitting 500 watts just yet, but we're getting very close to it. Anyway, I'm just gonna break the power monitoring and see if that helps. Now, this that I just changed, this doesn't affect the voltage regulator. It just affects what it reports to the GPU driver. So it breaks the software power monitoring, but the voltage regulator itself still knows exactly what's going on. So it's not really like, it's not like super sketchy or anything. Like, yeah, like I wouldn't consider it super sketchy. Like there's other ways of like skewing power readings from voltage controllers that are way sketchier than just setting that really low. Anyway, so let's run again. I think if I water cooled the card, 34,000 would probably be pretty easy to reach. Wait, I forgot to hit apply. Oh no, I think I just clicked on it, didn't I? Whatever. And I bet it didn't change. Yeah, that didn't do anything. Can't say I'm surprised. Um, I wonder. Thing is, I'm pretty sure if I touch the voltage offset at this point, it's just gonna crash. I guess we could try lower the V droop again. Not really thrilled about the voltages I'm seeing on the oscilloscope at this point, though. We're at 109 on the hotspot. If it wasn't such a pain to recover from a crash on these cards, or really, like, which actually would be completely solved if the boost algorithm just wasn't a thing. Because the whole issue is, like, after you crash, the boost algorithm is liable to just, like, derp out. Yeah, so if it didn't have a silly boost algorithm, then that wouldn't be a concern. Well, now we might actually hit over 750 watts. Admittedly, that, like, again, system power at the wall, so power supply losses included, 760. Ooh, boy. Well, it better score good, because it sure ain't power efficient at this point. Hey, and that made the score go down. Yeah, so I think now the boost algorithm's, like, starting to get annoyed at the temperatures, probably. Yeah, because we hit 110 on the hotspot. Max clock actually managed to go up ever so slightly. One thing I've been wondering with this card is if you ran some kind of super old 3D benchmark. So you know what? We might quickly hit it with Fire Strike, because that's my favorite 3D mark. I'm kind of wondering... The one issue, though, is because the boost algorithm on these is so clever, you have to basically tune the card per benchmark. So there's like a decent chance if we hit it with Fire Strike right now, it's just gonna crash. Um, and bring the V droop back up to, actually I think it was 65% that was doing best, so we'll go to like 66. Now we're just gonna lower this a tad because that's my main concern, is that this slider would cause it to crash in Fire Strike. Because I'm wondering if we run Fire Strike, could we actually get a higher frequency? So we're just gonna run 1080p. The one issue I could see is that like if you run a really old 3D benchmark, the card might not even like it might decide that whatever you're trying to run is too CPU bottlenecked to boost fully, right? Which is another sort of issue with, yeah, like, oh, come on, ramp. Yeah, we're at 300 FPS, the 90, like, we're on a 9700X. I think it's bottlenecked. It's probably really, really CPU bottlenecked. Fire Strike is not exactly Ryzen CPU friendly at the best of times, and we're running at like 400 plus FPS on a 9700X. So, like, I have the memory overclocked, but that's not gonna save it. Like, Fire Strike is not Ryzen. Like, the 90. If we were on a 9800X 3D, it might be okay. Then again, being CPU bottlenecked might give the card more headroom to boost. So who knows? But yeah, like this is not pulling as much power as it probably should be. I guess we could try run a higher resolution version of Fire Strike, but then we end up in that opposite, like if the goal is to get the highest possible frequency readout, that might actually be counterproductive if we put more load on the GPU. And unfortunately, we can't just use the GPU Z render test because that isn't heavy enough. So I did escape out of that because I was wondering, hey, we actually got 3475. So my theory was correct. If you just run something really, really easy, oh wait, no, that's the limit. Oh no, it didn't do anything. Okay, so it doesn't want to boost any higher. Well, yeah, and that's the kind of thing that you can do with a 9070 or even a 9070 XT. Like all of these modifications also apply to a 9070 XT. You're just not going to see as much of a massive like, performance improvement because if we look at like my very very first score that I ever got with this card, right? That would be yeah, probably this. Hello? Yeah, so you can see RX 9070, and this was like stock, like bone stock. Very first time I ever ran the card, right? And with everything we've done here, I can get scores like... Because it was the second to last one that was the highest, right? Yeah, we can... Which is... if I pull up a calculator... Because I can't do that in my head. So 33531 divided by, what was it, 26? I think it was 26765 or something like that. Yeah, so that's like a 25% performance improvement. But you're not gonna... I don't think you're gonna get as much of an uplift on a 9070 XT doing this thing, because the 9070 X... Like, the... Sort of one of the reasons why I chose the 9070 is because I knew from the get-go that, like, the power limit is way too low on these cards, in my opinion. So, like, out of the box, they're actually pretty power limited. Whereas 9070 XTs aren't, right? So, you're not starting from, like, a... Like, you're starting from a higher point with a 9070 XT compared to a 9070. Now, admittedly, 9070 XTs max out at higher scores because you do have a bunch of extra cores, but your starting point is already higher. And the disparity in like stock power limits is bigger than the core count, I think. Because this is like this card from the factory is a 245 watts, right? Whereas 9070 XTs, I think the base models are 304. So yeah, there's like a 24% difference in power limit between the 9070 and the 9070 XT, but there's only a because it's like 496 versus 3584. Where's GPU Z? Yeah, 3584. But there's only a 14% difference in core count, right? So like a big chunk of the performance difference between a 9070 and a 9070 XT is literally just the power limit. Because the core count on its own is not really like significant enough to make that much of a difference, which is why AMD power limits the 9070s so much. And that's also why I chose the 9070, because it's more fun to, like like it's more fun to like overclock a card that like starts really like starts out slower than a card that's already fast, and then it's like barely, and then it doesn't really gain that much. Not that it makes that much of a difference. Ultimately, the methodology would be basically the same. But I think it's cooler to go like, oh, look, I can squeeze like, what, 25% more FPS out of a 9070, whereas on a 9070 XT, it might be like 20% or 15. I don't have a 9070 XT, so I don't know how much it would actually be. So, yeah, anyway, that's it for this feature-length movie of a video. I don't know what made me think that there'd be any chance of me making something like this fit in 30 minutes, but I am bad at estimating how long things take to do, so I don't know what I expected. Anyway, hopefully you found this somewhat interesting, if not particularly useful, because yeah, like while you could technically hook up the Elmore EVC2 to your daily system and then reapply your like overvoltage settings every single time, one of the issues with this is that you kind of need to teach the boost algorithm about the higher voltages. Like if I clear the settings right now and then just reapply all of my Elmore EVC2 settings, like if I power down the system fully, because if I restart the system, it doesn't wipe the voltage controller, but if the system fully shuts down, that resets the voltage controller. So if we fully shut the system down and then turn it back on again, and then I reapply my settings in the AMD GPU driver, and I reapply my settings on the Elmore EVC2, and I go to run TimeSpy, it'll probably just crash. Which might sound completely insane because it's like, it's the same settings. How could it not be stable? And the reasoning is basically the process of like slowly walking the voltage up to like the point we ended up at, like teaches the boost algorithm how to like run at these higher voltages. And so if you just skip to high voltage without the whole like teaching process, it just crashes, which is, yeah, I mean, still less, from like still less annoying than what Vega does, but I miss the days of GPUs just having a proper core clock setting. Anyway, yeah, so that's it for the video. So I guess hopefully you found it entertaining, because I don't know that it's very useful. And if you'd like to support the channel, there are links in the description that you could check out, which would be very much appreciated. And that's it. So thanks for watching, and goodbye.